everyone, this is the 44th lecture of the course on principles of behavioral economics. We are discussing intertemporal choice models, and in this module we are going to discuss discounted utility model. We have already talked about Baum-Bawerk's trade-offs and Irving Fisher's indifference curve analysis. They were early pre-DUM, that is discounted utility model developments in the theory of intertemporal choice that took different psychological factors into account that were swept away by the DUM, condensing them into a single construct, the discount rate. Samuelson introduced the DUM in 1937 in a short article modestly titled as A Note on Measurement of Utility. Apart from commenting that the comparison of intertemporal trade-offs required a cardinal as opposed to ordinal measures of utility, it extended Fisher's indifference curve analysis, essentially limited to the comparison of two periods to multi-period situations. So, giving basically a more formal structure to Irving Fisher's indifference curve analysis, extending it to multi-period situations. The nature of the model can be best described in mathematical terms. It specifies an intertemporal utility function where utility is a function of consumption spread over t periods, which describes the utility at time t of the consumption profile starting in period t and continuing up to period capital T. So, you can see that Ct, Ct plus 1, Ct plus 2 and so on, T can take any values. The model incorporates the general axioms of the neoclassical model described in previous modules regarding the completeness, transitivity and independence principles. These principles we discussed in the context of the prospect theory. The DUM then goes on to assume that a person's intertemporal utility function can be described by the following specific functional form. So, this is the functional form where dk is equals to 1 upon 1 plus rho raised to the power k. Now, if you remember in the previous modules we have talked about a discount factor of 1 plus r. This was for one period. For two periods that would be 1 upon 1 plus r raised to the power 2. So, in a similar fashion we have here 1 upon 1 plus rho raised to the power k. R is replaced by rho. We call it the discount factor. What they are discounting? They are discounting the future flow of utilities arising out of consumption. This implies that d naught equals to 1. So, if dk is 1 upon 1 plus rho raised to the power k, then when k is equals to 0, then d 0 equals to 1. Then d 1 would be 1 upon 1 plus rho and so on. Therefore, we have this expression, this is the original expression which can be expanded, and when dk is replaced by this expression, then we have Ct. First of all, see this can be expanded as d naught u C t plus 0, t plus 0 is basically t. Then d 1 u c t plus 1 and so on. So, d naught is 1, that is why we have only C t, or we can also write it as u c t. We are assuming here that utility depends on utility, say it is a linear function of consumption. So, u c t equals to C t. In a similar fashion we have d 1 equals to 1 upon 1 plus rho. So, C t plus 1 upon 1 plus rho and so on. The term u c t plus k can be interpreted as the person's instantaneous utility function, that is their perceived well-being in period t plus k. The term dk refers to the person's discount function, that is the relative weight that the person attaches in time period t to their well-being in period t plus k. Finally, the term rho refers to the person's discount rate, that is the rate at which they discount expected future utilities. This term therefore combines all the various psychological factors involved in time preference that were discussed earlier. It will aid an understanding of the workings of the model as well as the implications and anomalies discussed later if a simplified example is examined at this stage. Let us take the following consumption profile measured in thousands of rupees per year over a period of the next 3 years 20, 20, 20, which implies that every year you are going to spend 20,000. We will also assume for simplicity that these consecutive equal amounts of consumption yield equal amounts of utility. So, again this is a simplistic assumption. If UCT or UCT equals to CT, alternatively U20 is equals to 20. Since the measurement of utility is an arbitrary units of utils or utiles, we can consider the utility profile as consisting of the terms 20, 20, 20. It is assumed that the model is discrete and that the utilities are all received at points in time at the end of each period rather than being continuous flows throughout each period. So, basically if this is 3 years, then you are receiving the first 20 at the end of first year, the second 20 at the end of second year and the third 20 at the end of third year. This may appear unrealistic, but the DUM can be modified to transform it into a continuous time model as well. The utility function becomes an integral of a negative exponential function. We will use the discrete form of the model for the time being. If the consumer discounts future utility at the rate of 10% per year, the current utility of the consumption and utility profiles can now be calculated as, see, the first period it is 20 divided by 1 plus 0.1. So, we are beginning with period 1, not considering period 0, specifically because the 20 is coming at the end of the first period. So, that is why this is raised to the power 1. Then at the end of second year we have 20 divided by 1 plus 0.1 raised to the power 2, and then this is raised to the power 3. By summing all of them, this is 49.74. This calculation illustrates an important feature of the DUM. It closely resembles the compound interest formula used in calculating net present value. This, analog with the common technique for evaluating financial investments, has been largely responsible for the rapid assimilation of the model by economists. Koopmans in 1960 showed that the model could be derived from a set of axioms or basic principles that are superficially plausible. The model also gained normative status as it was shown that an exponential discounting function was consistent with rationality in the sense that it resulted in dynamically consistent choices. So, since this model was leading to rational decision making, so it also gained the normative status. Other economists including Lancaster, Fishburne and Mayer have since provided alternative axiom systems for the DUM, further increasing its perceived legitimacy and popularity. Now, what Samuelson proposed, the mathematics of exponential utility model. We have U C naught C1 equals to, so basically the total utility from consumption across 2 periods is the utility from consumption in period 0 plus consumption in period 1 multiplied by the discount factor. So, here UCT is a period utility function for period t and the future utility is discounted by a positive number delta, which is less than 1. Here delta is the discount factor. Let u prime c denote the derivative of uc. Then I will be having delta u c naught c1 upon delta c naught is equal to u prime c naught. So, this is again, if you remember in the previous, probably the second module, that this is the partial derivative with respect to consumption is in period 1, where we are trying to find out that if only the consumption in period 0 changes, holding the consumption in period 1 constant, then how total utility is going to change, and this is denoted by u prime c naught. And in a similar fashion, this is the partial derivative with respect to consumption in period 1. So, only consumption in period 1 is changing, and how this is impacting the total utility. We denote it by u prime c1, and since this has a delta in front of it, so the delta remains here as well. Therefore, u prime c naught divided by delta u prime C1 is equal to 1 plus r is the Euler equation for the time discounting model, and this relationship was derived in module 1 or 2 or module 41 or 42, that is the initial modules of the on the intertemporal choice models. Here the left hand side the ratio of the utility in 2 periods, while the right hand side is the ratio of the prices of their prices. So, this also we discussed that 1 plus r is basically the relative price of consumption in period 1 and 2. The 2 period model is easy to understand and to analyze, and for some application problems the insight we obtain from a more general multi-period model with 3 periods and more may be essentially the same. For other application problems, however, results from a 2 period model may not be appropriate. For example, consider a business person who will retire in 3 years. He is thinking about how much to consume and save this year. One option is to enjoy consuming much this year and to start to save for retirement in the next year. This option looks attractive, namely there is a temptation to procrastinate saving for retirement. In order to think about this type of problem, it is necessary to use models that deal with 3 periods or more. Let us look at a multi-period model. The budget constraint equation would be something like, initially we had only these 2 periods, now that is extended to t periods. So, we simply keep on writing them with 1 upon 1 plus r raised to the power capital T multiplied by Ct, and this consumption over a large number of periods, multiple periods, must be equal to the present value of all the income streams across all the periods. This intertemporal budget constraint is similar to that of the 2 period model in that it states that the discounted present value of current and future consumption must not exceed the present discounted value of current and future labor income. The consumer in a multi-period model maximizes his utility function, again the utility from all the consumption spread across all possible years, subject to the intertemporal budget constraint. The Euler equation for this optimization is, now we are basically equating like delta u delta C t plus k upon delta u delta C t, which is essentially, I mean this is what is written, they are the same two things. Delta u delta C t plus k is u prime C t plus k, and then we equate them with their relative prices. So, this is 1 upon 1 plus r raised to the power t plus k, and the relative price of this is 1 upon 1 plus r raised to the power t. Then cancelling things out, we have 1 upon 1 plus r raised to the power k. This Euler equation shows that the marginal rate of substitution of consumption in period t and consumption in period t plus k is equal to their relative prices again, and here the relative price is 1 upon 1 plus r raised to the power k. As the time discounting utility function for a multi-period, we consider this stream of utilities. So, u c naught plus delta u c 1 plus delta square u c 2 and so on. So, now what is the difference? You can see that 1 upon 1 plus r is replaced by delta, or which we are actually calling 1 upon 1 plus rho here in this module. We call this exponential discounting model because the utility from period t is discounted by the exponential function delta t of delta raised to the power t of delta. In this model, the Euler equation that equates the marginal rate of substitution of consumption in period t and consumption in period t plus k to their relative price is simply 1 plus r raised to the power k. So, actually if you remember the Euler equation, then initially we had it with just 2 periods. So, we had u prime c t in the numerator and delta u prime c t plus 1 in the denominator, that was set equals to 1 plus r. Now, we have delta raised to the power k because we are comparing basically the marginal rate of substitution between period t and period t plus k. So, in the previous case k was equals to 1. Now, we are generalizing it to any value of k, as a result of which we have delta raised to the power k u prime c t plus k, and this is equals to 1 plus r raised to the power k. If we set k equals to 1 in this equation, then we obtain the Euler equation for two neighboring periods with which we are already pretty much familiar. In traditional economics, especially in macroeconomics, the exponential discounting model has been used as the standard model. Both the permanent income hypothesis and life cycle hypothesis, which are the key consumption theories in macroeconomics, depend on the above equation. As a simple case, we assume that delta into 1 plus r equals to 1. Here delta into 1 plus r is coming from that Euler equation. We had u prime Ct divided by delta raised to the power k u prime Ct plus k equals to 1 plus r raised to the power k. This implies that u prime Ct divided by u prime Ct plus k is equal to delta raised to the power k 1 plus r raised to the power k, right. And if k is equal to 1, then this would become delta into 1 plus r raised to the power k. So, if we assume that delta into 1 plus r equals to 1, then the marginal utility does not change over two neighboring periods. If this is equals to 1, if we set this equal to 1, then what we have is that u prime Ct equals to u prime Ct plus 1, right, because here k is equal to 1, here k is equal to 1. So, this implies that the marginal utility does not change over two neighboring periods. The marginal utility is thought to satisfy the law of diminishing marginal utility, that the marginal utility decreases as consumption increases, and that is how we have u double prime c less than equal to 0. That is, the second derivative of the utility function is less than equal to 0. Here we assume that the strict inequality in this context, if it is not changing, then this means u double prime c equals to 0 holds. Then in order for the marginal utility to stay the same over two neighboring periods, consumption should stay the same. Because this holds for all two neighboring periods, consumption does not change in all periods. In the budget constraint equation, this is the budget constraint equation that we have, we can let Ct be constant at C and solve for C to obtain the optimal level of consumption. So, all these C's will be replaced by a single C, and accordingly we can solve for the optimal level of consumption, which is going to remain fixed for all the periods. The optimal level of consumption depends on the right hand side of the budget constraint equation, which is the present discounted value of current and future labor income, which is basically the permanent income, and not on income in each period beyond its contribution to permanent income. The permanent income hypothesis applies this model to response of consumption to temporary changes in income due to business cycle fluctuations and other such factors. Even when income decreases much because of a recession, as long as the change is temporary, consumption should not change. So, this is the basic precepts of permanent income hypothesis or the life cycle theory that we had discussed while discussing mental accounting. And as a result of which there would be some drop at some point of time when the change is temporary. We can expect that there would be some other point of time when this drop would be made up for, and as a result of which overall the consumption is or are expected to remain the same. The consumer is predicted to borrow or draw funds from assets that he has accumulated in order to keep consumption at the same level. The life cycle hypothesis applies this model to the whole life of a consumer. Even when income is low during school years and retirement years, consumption is predicted to be the same as in work years. When the interest rate is high and delta into 1 plus r is greater than 1, then u prime Ct is greater than u prime Ct plus 1. Because the marginal utility decreases over time, the optimal level of consumption is predicted to increase over time. Alternatively, this implies that when borrowing is expensive, then people borrow less. So, with this I conclude this topic on discounted utility model. Thank you.